Okay, and we'll take a same numerical and you will know about all these things. Okay, so as you know, so I will just once again I will repeat all these things. So flexibility method. Okay, the flexibility method. Yes, what is the other name for flexibility method? Compatibility and one more force method. Correct. And force method. So the flexibility is displacement per unit. Stiffness is what? Force per unit displacement. This is displacement per unit force. So here what we are finding out the P force and the inverse of this flexibility matrix and in bracket total displacement at that coordinate minus displacement at the displacement due to the loading. So we are using this one to calculate the unknown forces in the indeterminate beam. Okay, this formula we are using. So no. And the unit load method generally used in the flexibility approach to find out the deflection, or we can call as a displacement, because we want a displacement. Here also the flexibility approach is nothing but what we have the displacement. Okay, when we have unit force, what is the rotation and the deformation at the along this coordinate, that is delta 1 1. Okay, this is also a displacement. So the displacement we can find out by using a unit load method. Okay, so yesterday I told this is a formula m divided by ei into ds to find out the deflection, now this is very easy method to find out the deflection, because sometimes it is very hard to find out the displacement by using our regular method. Correct, that is what slope, and generally what, when there is a rotation we have the slope at the end, we can find out the slope. But when there is a load, okay, at somewhere a and b, how to find out this slope and deflection under this load? It's very difficult, it's very difficult. So that's why we have a unit load approach in the flexibility method. Okay, so if you remember, okay, one thing, if you remember this numerical, because in flexibility first numerical we have covered, there is a cantilever beam and we have roller support here and we have roller support here. Okay, and we have 240 kilonewton and 120 kilonewton load A, B, C, and the spans of all the beams are 5 meter, 5 meter, 5 meter, 5 meter. So this is we have to solve by flexibility method or force method or compulsion method. Okay, so we know the degree of static indeterminacy we are finding out, and degree of static indeterminacy for this one is 2. Correct. So as we know in the flexibility approach, our formula is to calculate the forces and the inverse of flexibility matrix, and we have the displacement at the coordinate minus the displacement due to the loading along the coordinates. This is our formula. Now, so degree of static indeterminacy, now we have to release this structure. Okay, you can release like this also. You keep make the coordinate like this, coordinate 1 and coordinate 2. Reaction as a coordinate. Now the reaction as a coordinate I have taken, okay, and I have released structure. That means we have two equilibrium equation. If we know these two forces, we have only one vertical and the moment we can, by using equilibrium method, we can analyze this beam. Now if I use this coordinate, because always in unit load method, remember in unit load method you can make this reaction as a coordinate. Now if I make the reaction as a coordinate, so yesterday I told there is one table in the unit load method. Yes, that what was, so we have a portion of a beam. Now here what A, B and C, correct? So we have two of a beam, but here we have the point loads, that's 240 kilonewton and 120 kilonewton, 5 meter, 5 meter, 5 meter and 5 meter, all the beams having the same I, correct? So whenever there is a point load or the movement, so you divide this beam, okay? So I will divide this beam here D and here E. So the portion of a beam, what will be the CD, or we have coordinate 1 and coordinate 2. So you divide this beam, okay? DB, BE and EA, correct? Then next is origin, sorry, moment of inertia. The moment of inertia is different now, but it is same I. Now next is what? The length means origin. First we have to maintain the origin. For C, if you are taking from left to right, C is origin, here D is origin, E is origin. Now next is what? To solve the integration, what is our formula? The formula is m divided by EI into ds. So we have to put the limit for CD, what is 0 to 5, again 0 to 5, 0 to 5, 0 to 5, correct? Now next one is, moments due to the load. Okay, remember now, see carefully here, movement due to the load. Now along the CD, correct? If I take a section here, x and it is x, there is no external load on the CD, so the moment due to load is 0. Now next, CD as origin. If I take a section here and this is x, what is the moment due to the load? 120 into x, 120 into x. Okay, assume clockwise positive. Okay, now next, correct? There is no other load. Next one. Now if I take a BE as a span and I will take a section and B as origin, x from the B, what is it loading due moment due to the load? 120 x plus 5, 120 x plus 5, correct? And for EA, if I take a section here and E as a origin, so 120 x plus 10 plus 240 x, 240 x, this is the moment. Now m1 is what? Due to the coordinate 1. Now this along the coordinate 1 we have this load, correct? What is the moment due to this coordinate 1? m1. So here there is no load, so 0. For here also there is no load, 0. Now here for this section 1 into x, it is anti-clockwise, so minus x. And for EA, E is the origin. If I take a section x here, which gives us moment 1 into x plus 5 minus x plus 5. And M2, M2, M2 is what? Due to the 2. If I take a section here, what is the moment due to this force? 1 unit load. Unit load means along coordinate 1 I have applied unit load and along coordinate 2 I have applied unit load. So 1 into x minus x. You are getting my point? Now next one is, if I take a section, now D as origin, but unit load is at along coordinate 2, so what? X plus 5 minus x plus 5. Now for EB, if I take a section here, this load gives x plus 10 minus x plus 10. Now coordinate 2 here minus x plus 15. Yes, you have any doubts? No, it is you make it clear. It's very important now. You have any doubts? You have any doubts? Students, I'm asking you, you have any doubts? Yes, you have any doubts? Now, how to, or if you don't know, I will put. Now, if I want to find out, now, see here. P, flexibility inverse, displacement at the coordinate due to loading. So we have two P1 and P2, and here we have delta 1 1, delta 1 2, delta 2 1, delta 2 2, inverse of this matrix, displacement at coordinate 2, displacement at coordinate 1 and 2 minus delta 1L, delta 2L, correct? So how will get delta 1L? Delta 1 n means what is the displacement along the one coordinate 1 due to the loading. Okay, now simple. So m1 and ml, multiply these two quantity moments, divided by ei into ds. Simple, to find out this deflection. So how we'll get? Now we'll find out. So multiplication of both these two. Okay, so what is m1 and ml? The first one is 0, correct, plus for dB span 120x into 0. Next one is 120x plus 5, okay, multiply by minus x into dx divided by ei integration 0 to 5 plus integration of 120 x plus 10 plus 240 into x multiply by minus x plus 5 divided by ei into dx. So this is okay. 0 multiply by 0 0. So we'll solve this one. 0 to 5, 120x plus 120 into 5, 600. 600 into minus x dx divided by ei plus 0 to 5. We'll multiply this term. 120x plus 1200 plus 240x multiply by minus common x plus 5 minus common. So minus common from the both the terms, integration of 0 to 5, 120x square plus 600x divided by ei into dx plus 0 to 5, 120x square plus, sorry, okay, no problem, 1200x plus 240x plus 600x plus what is the next one? 12 and 60 plus 1200x dx. So what will be the minus 0 to 5, 120 it becomes 240x square plus 1 2, this is x square, no, 480, 480x square, 600, 1800, 1200, 1 2 3 plus 36x. If I'm somewhere wrong, just correct me. The and next one will be 6000 dx. Now what is the answer? Tell me. So delta 1L equals to, divided by EI is common, okay, 1 by EI somewhere. This is also divided by EI. This is also EI. So what is total is 20 plus 45 plus 30. 95 minus 95 divided by EI. Students, you got this answer? Okay. So delta 1L. So similarly, you can find out delta 2L. So delta 2L equals to what? Integration of M2 ML divided by EI into dx. So delta 2L equals to, now we have to multiply this and this one, this and this one, correct? So first 0 I will not take, second one 120 x minus x plus 5, 0 to 5 plus, next is 120 x plus 5, x plus 10, all are negative, EI is common, 0 to 5, and the last no, sorry, last one 120 into x plus 10 plus 240x in another bracket x plus 15 minus common, correct? So EI is same, sorry, EI. So I will make minus 1 by EI common. 0 to 5, 0 to 5, 0 to 5, all our integrations are same. So I will make 0 to 5 common, and I will multiply these terms, 120 x square plus 600 x plus, so this bracket, it is what, 120 x plus 600, correct? So 120 x, if I multiply by x, 120 x square plus 1200 x plus 100 x plus 6000 plus. Now this term will be 120x plus 1200, correct? 1200 plus 240x. So this term becomes 360x plus 1200. So I can make, if I multiply here, 360x square, 360x square plus 360 into 15, 5400 x plus 1200 into x plus 1200 into 15, 1800 into dx. Now I will make terms clear, 0 to 5, 1, 2, 3, 120 plus 120 plus 360, 600x square plus 1, 2, 600 plus 1200 plus 600 plus 5400 plus 9000x plus 6000 18,000 2400 into dx. Now minus 1 by ei 600 x cube divided by 3 plus 9000 x squared divided by 2 plus 24000 into x, limit are 5 to 0. Minus 1 by ei So this is 25,000. This is 112500 plus this one is 12000. So delta 2L equals to minus 257500 divided by EL. Divided by EL. Correct? Now, so now what is the next piece? Displacement delta 1 we have to find out. Delta 1 that means what is the displacement at 1 due to the unit load applied at coordinate 1. So same 1 so what will be the m1 multiplied by m1 divided by ei into dx. M1 0 no minus x plus 5, so I will write minus x dx divided by ei 0 to 5 plus 0 to 5 minus x plus 5 multiply by minus x plus 5 because m1 multiply by m1 divided by ei into dx Now 1 minus 1 sorry 1 by ei common because minus minus become positive, minus minus become positive. 0 to 5 x square plus x square plus 10x plus 25 divided by ei common into dx. Correct? So how if you solve this one, so delta 1 divided by ei, it becomes 0 to 5 2x square plus 10x plus 25 dx. So delta 1 equals to 1 by ei 2x cube divided by 3 plus 10x square divided by 2 plus 25x, limit are 5 to 0. $83.33 125 plus 125 delta 1 1. Correct? Just check. And delta 1 2 and delta 2 1 are same because we have diagonal matrix delta 1 1 delta 1 2 delta 2 1 delta 2 2. So this is diagonal. Upper matrix and lower matrix will be the same because it is a symmetrical matrix. So I can take delta 2 1 and delta 1 2 is same. So m1 multiplied by m2 or m2 multiplied by m1 is same. So 0 to 5 m1 m2. So 0 into x divided by ei into dx, first one. Next is 0 to 5, 120x minus x plus 5 divided by ei into dx. Next is 0 to 5, 120x plus 5. Sorry. I have taken wrongly. M1, M2 we are multiplying now. So M1 is M1 is 0. Here we have minus x. First for CD, for DB 0 to 5. We have 0 minus x, minus in bracket x plus 5 dx divided by ei, plus next one is BE 0 to 5 minus x minus in bracket x plus 10 dx divided by ei, plus 0 to 5 minus in bracket x plus 5, correct, another bracket minus x plus 15 dx divided by ei. So what will be this? This one cancel, it is multiplied by 0. So what we have, this one 1 by ei common, minus minus become plus, 0 to 5 integrations also same, x square plus 10x plus x square plus 15x plus 5x plus 75 dx. So 1 by ei. So here it is lengthy procedure, we have to solve the integration, but it is very easy method. 0 to 5 2x square plus 20 30x plus 75 dx. So 1 by ei in bracket 2x cube divided by 3 plus 30x square by 2 plus 75x 5 0. So what is delta 1 2? So delta 1 2 equals to 833.33 divided by ei, and delta 2 1 also, delta 2 1 also. Now next one delta 2 2. So that is m2 divided by 0 to 5 for first one, minus x dx divided by EI. For next span of beam 0 to 5, minus x plus 5 in bracket, another minus x plus 5 divided by EI plus 0 to 5 minus x plus 10 minus x plus 10 divided by EI into dx plus 0 to 5. Last span is x plus 15 dx divided by EI. Now we'll solve this one. 1 by EI common, integration lower and upper limits are same, so I will take 0.5 common, minus minus become plus, not required to keep minus outside. So we have x square, this term here, x plus 5 square, that is x square plus 10x plus 25 plus x square plus 20x plus 100 plus x square plus 30x plus 225 dx. So 1 by EI 0 to 5 here become 1, 2, 3, 4. 4x square 1, 30, 60x plus 125 plus 225, that is 250, 350 into dx. So 1 by EI equals to 4x cubed divided by 3 plus 60x squared divided by 2 plus 350x 50. So 1 by EI 266.67 divided by EI delta 2 delta 2 delta 2. Now all the deflection. Now it's very simple. P delta 1, delta 1, 2, delta 2, 1, delta 2, 2, inverse of matrix displacement at the coordinate minus delta 1L delta 2L. So P1 and P2 is equal to, we'll take bigger one. So delta 1 is what? 333.33, correct? 330.33 divided by EI. This one is 833.33 divided by EI. 833.33 divided by EI. This will be 266.67 divided by EI, inverse of this matrix. So there is no settlements along in the given numerical. They are not given the settlements of joint B and C. So there is no displacement, final displacement at coordinate 1 and at coordinate 2 is 0, 0 minus delta 1L 95,000 divided by EI, divided by EI and minus 2,57,500 divided by EI. Simple. Inverse of 1 by EI is EI. So in bracket 333.33, 833.33, 833.33, 2666.67 inverse of this matrix, and this matrix becomes minus minus plus 1 by EI common 95,000, 2,57,500. So this EI get cancelled. So P1 and P2 are is equal to put. So what is the answer? One 199.3, 34.2, correct? So in this cantilever beam, this reactions along one coordinate is 199.3, along this one is 34.28, and the load is 120 kilonewton, and load is 240 kilonewton. Now what is, we can analyze this beam, we can find out this one and this one, A, B, C. Summation of Fy must be equals to 0. So Fa Fa plus 199.3 plus 34.28 is equal to 240 plus 120. What is Fa? 126.42. What is movement? Simple. Take a moment summation of movement about point A is equal to 0. So are all clockwise. So MA is equal to 120 into 15 plus 240 into 10, sorry 5 minus 34.28 into 20 minus 199.3 into 10. Correct? What is MA? 120 into 15 plus 240 into 5 minus 34.28 into 20 minus 199.3 into 10. 321.4 kilonewton meter. So this one becomes 321.4 kilonewton meter. So like this, we can analyze this continuous beam. So this is also called as a flexibility approach, but by using a unit load method. But by using a unit load method. Unit load method. Okay. So you can do by using this formula approach also. So like this, how we have solved in earlier. That means suppose this is a cantilever and we have roller support here, 120 kilonewton, 240 kilonewton, correct? A, B, C. So what we have done, the coordinate 2. So we have assigned the coordinates, correct, like this, cantilever, and we have released this structure. Correct? How we have solved? You can see in the first numerical I have explained this one. So you check the answers also. Okay. So what we got by this approach and this earlier approach is same. Okay. Okay, students, you have any doubts?